Welcome to MathGPT. Today we're going to learn about inductance, which is a fundamental concept in electromagnetism and circuit theory. Inductance is the property of an electrical conductor to oppose a change in the electric current flowing through it. There are two main types of inductance that we'll discuss today. First, self-inductance, which occurs when a changing current in a coil induces a voltage in itself. And second, mutual inductance, which occurs when a changing current in one coil induces a voltage in another nearby coil. Let's start by understanding self-inductance in more detail. Self-inductance is represented by the letter L and measured in henries, named after the scientist Joseph Henry. To understand self-inductance, imagine a coil of wire with current flowing through it. When electric current flows through the coil, a magnetic field is created around it. The magnetic field lines form closed loops that pass through the center of the coil. The strength of this field depends on the current and the geometry of the coil. Now, let's see what happens when the current changes. When the current in the coil changes, the magnetic field also changes. According to Faraday's law, a changing magnetic field induces an electromotive force, or EMF. This induced EMF opposes the change in current, as stated by Lenz's law. This effect is quantified by self-inductance L, where the induced EMF equals negative L times the rate of change of current. For a solenoid, which is a coil wound into a tightly packed helix, the self-inductance can be calculated using this formula. L equals mu naught times n squared times A divided by L, where mu naught is the permeability of free space, n is the number of turns, A is the cross-sectional area, and L is the length of the solenoid. As you can see, the inductance increases with the square of the number of turns, which is why inductors typically have many turns of wire. An inductor also stores energy in its magnetic field. The energy stored is given by 1/2 times L times I squared, where L is the inductance and I is the current. For example, if we have a 5 Henry inductor with a current of 2 amperes, the stored energy would be 1/2 times 5 Henries times 4 ampere squared, which gives us 10 joules. Now, let's move on to mutual inductance. Mutual inductance occurs when we have two coils near each other. When current flows through the first coil, it creates a magnetic field, and this field passes through the second coil. When current flows through the primary coil, it creates a magnetic field. Some of these magnetic field lines pass through the secondary coil. If the current in the primary coil changes, the magnetic field also changes. This changing magnetic field induces an EMF in the secondary coil, according to Faraday's law, which we discussed earlier. The mutual inductance M quantifies this relationship. The induced EMF in the secondary coil equals negative M times the rate of change of current in the primary coil. Several factors affect mutual inductance. The geometry and relative position of the coils are important. The closer the coils, the higher the mutual inductance. The orientation of the coils also matters. When the coils are aligned, more magnetic field lines pass through the secondary, increasing the mutual inductance. For two coils, the mutual inductance can be calculated as M equals mu naught times N1 times N2 times A divided by L, where N1 and N2 are the number of turns in each coil. In practice, not all magnetic flux from the primary coil links with the secondary coil. The coupling coefficient, K, represents the fraction of magnetic flux from one coil that links with the other coil. The coupling coefficient ranges from 0 to 1, with K equals 1 meaning perfect coupling, where all flux links both coils. The relationship between mutual inductance M and self-inductances L1 and L2 is given by M equals K times the square root of L1 times L2. Let's look at some common applications of inductance. Transformers use mutual inductance to transfer energy between two coils while changing the voltage level. Inductors are used as chokes in power supplies to filter out high-frequency noise. In radio circuits, inductors are used with capacitors to create tuned circuits that can select specific frequencies. Electric motors and generators rely on inductance principles to convert between electrical and mechanical energy. Let's summarize what we've learned. Self-inductance is the property of a coil to induce an EMF in itself when current changes. Mutual inductance is the property where changing current in one coil induces an EMF in another coil. For self-inductance, the formula is E equals negative L times d/dt. for mutual inductance. The formula is E2 equals negative M times d1/dt. Thank you for watching. I hope this helps you understand the concepts of self and mutual inductance.